You've probably heard of the terms big data and artificial intelligence. And perhaps you've also heard of machine learning or even deep learning. What do these terms stand for and how are they related? In the figure to the right, you see a Venn diagram. Big data is the more popular term for what I call data science. This is the scientific discipline that studies everything that is related to data, from data acquisition to data storage, transporting data over networks, data analysis, data visualization, searching through data, making decisions based on data, and determining how to create value from data for companies. This field is very large, even larger than computer science itself, also involving fields such as economics and mathematics. A subset of data science is artificial intelligence. Artificial intelligence is concerned with making machines smart. This involves fields like robotics, natural language processing, information retrieval, knowledge representation, computer vision, and machine learning. The field machine learning aims to develop algorithms that become smart through learning from historical data. This means we feed an algorithm data, which then in turn changes its own programming to become better at a certain task. The most prevalent task is classification, where one tries to assign the input, say an image, to a particular category, say an apple or orange. Here one has access to input data, the image, as well as target labels, apple or orange. But this is not how we learn to understand the world around us. Instead, we learn to understand the world without having access to labels, which we call unsupervised learning, or by interacting with the world and receiving rewards from it, which we call reinforcement learning. A dominant modeling paradigm in machine learning is what we call graphical models. When we use graphical models, we usually assign probabilities to all our variables so that we can compute the probability that some event happens given that I have observed that other events have happened. For instance, what is the probability that I have the flu given that I have a headache and a sore throat? One advantage of graphical models is that they allow us to model the physical processes and causal relationships by which the data was generated. This way we can conveniently inject our expert knowledge into the model. On the opposite side of the spectrum are purely data-driven models. Deep neural networks are one example of this class of models. Neural networks are highly flexible models, but they do not simulate the physical processes that generated the data. Instead, we say they let the data speak. You typically need a lot of data to train neural networks, but the advantage is that they are not constrained by our limited imagination of what the data generating process was. The first neural network was invented at the dawn of AI itself. In 1943, McCulloch and Pitts defined an architecture that was loosely inspired by biological neurons. The basic design is shown to the right. We present an input, or data point, to the first layer of neurons, who multiply the numeric value of the input with a weight, and then add up these weighted values at the output neuron. The output neuron turns on when this weighted sum surpasses a certain threshold, indicating that the input belongs to a certain category. By presenting many example input-output pairs to the artificial neural network, it can adapt its weights and thresholds to predict the correct categories. After some initial excitement, people largely abandoned this idea because it was found that the McCulloch and Pitts model could not solve certain rather basic problems. This period is known as the first neural network winter. In the 80s, however, people discovered how to effectively train a two-layer neural network with many McCulloch and Pitts modules operating in concert, shown in the figure to the right. The middle layer of artificial neurons is now not observed, hence the name hidden layer. Each hidden unit represents an abstract feature, say a nose if we want to recognize a face, that can be detected in the input. The combination of these features then determines if the input belongs to a particular category. The signal that propagates through the neural network can be visualized as follows. Each neuron is a small light bulb that looks at all connected neurons below it to decide if it should turn on, where some neurons have more influence than others. If enough neurons below it turn on, it will itself turn on and provide a signal to the neurons above it. As you can see in the figure to the right, each neuron turns on if a certain pattern in the input was detected, and neurons deeper in the network encode for more abstract patterns. The trick that allowed researchers to learn these models effectively from data was a simple bookkeeping device based on the chain rule when computing gradients. This backpropagation algorithm, as people call it, propagates the error computed at the output of the network back through the network towards the adjustable weights, providing the signal to update them in a way that makes the whole network perform better. After some initial successes, alternative methods such as support vector machines claimed the center stage, heralding a second neural network winter. These new methods succumbed to a much more rigorous theoretical analysis and had comparable performance. But in 2009, neural networks once again rose from the grave when Geoffrey Hinton and his team in Toronto trained deep neural networks with many layers of hidden units and applied them to the problem of speech recognition, an application domain that had been stagnant for many years. Through the application of deep neural networks, an amazing improvement was established, paving the way to speech recognition on your smartphone. A few years later, deep learning also swept away all competition at the annual Computer Vision ImageNet Challenge. And this year, 2016, we have already witnessed two stunning results. Microsoft reached human-level performance at the ImageNet competition using a network with 152 layers. And Google DeepMind beat the world champion Lee Sedol at the game of Go 4-1. By now it's undeniable that deep learning is a powerful tool in the machine learner's toolbox and will find its way to many exciting applications in the future. So why do these neural networks perform so well? The reason is a confluence of three factors. Researchers have found that deep neural networks can be trained very efficiently with graphics processing units, or GPUs. A GPU was originally developed to display video on a computer screen, but now serves as a miniature supercomputer for deep learning. The second reason deep learning is taking off is the availability of massive amounts of big data. Besides the digital footprint we leave on our computers and cell phones, sensors are being installed in our homes, our cars, and our workspaces. This Internet of Things creates petabytes of data that is uploaded into data clouds where it can be analyzed. Deep learning models are able to leverage these large amounts of data effectively by entertaining millions of freely adjustable parameters. The largest networks boast billions of parameters, and since bigger and deeper networks seem to imply better performance, the architectures keep growing in size every year. The final reason for deep learning's success is some new ideas on how to train the networks effectively, avoiding issues such as the vanishing gradient problem, where the learning signal in deep networks becomes too faint when propagating the error back through the network layers. So in summary, it's big computers, big data, and big models that are the basis of the recent successes in this field.